Okay, we are back again. Now, next is that parallel resonance, that is two branch circuit. We have taken a simple two branch circuit, right. So, your this is RL L, that is one inductive branch, and this is one capacitive branch, right. So, it is RL L omega and it is RC your XC, right. So, this is we have to see the parallel resonance of this circuit. So, y is the admittance, right. So, y is equal to your y is equal to that admittance is equal to YL plus YC, right. So, YL is that admittance of this inductive circuit. So, it is 1 upon RL plus JXL, and this is your plus 1 upon RC minus JXC, right. So, now this one numerator and denominator, this one you multiply by your RL, this term you multiply by your RL minus JXL, that means this one will be RL minus JXL, right, divided by RL plus JXL into RL minus JXL, that is RL square minus J square XL square. So, J square is minus 1, so it will be your RL square plus your XL square. So, just separate it, it will be RL upon RL plus XL square, and this one your what you call, this will be your here it is taken common. So, it is minus XL upon RL square plus XL square, imaginary side, right. So, this is actually these two are real part. So, real part is RL upon your RL square plus XL square, and imaginary part is minus XL upon RL plus XL square. So, here it is minus XL upon RL plus XL square. Similarly, for RC minus JXC, numerator and denominator you multiply by RC plus JXC. So, real part is here and imaginary part is here, right. So, let me clear it. So, this means that means circuit is at resonance when the complex admittance is a real number. That means this one, this imaginary part you set it to 0, this one you set it to 0. If you do so, it will become XC upon RC square plus XC square is equal to XL upon RL square plus XL square, right. This is actually at omega is equal to, this is at omega is equal to omega 0, the resonance frequency. That is why that wherever we make it XL is equal to L omega, that is your L omega 0, right, and XC is equal to 1 upon omega C, that is your 1 upon omega 0 C, right. So, this one you put it here, that XL is equal to your L omega 0 and XC is equal to 1 upon your omega C, that is omega 0 C, and just simplify, right. Let me clear it. So, this way if you just simplify, that is all, right. Cross multiply, this one you cross multiply and then you put it. So, each of the 5 quantities in equation may be made variable in order to obtain resonance. There are 5 variables, right. There are 5 variables. One is omega 0, then C, then RL, then RC, then L. So, there are 5 variables, right. So, in this case, that each of the 5 quantities in equation 2, right. So, this is equation 2, this is equation 2, right, may be made variable in order to obtain resonance. Now, solving equation 1, that means rather than I will say equation 1 or equation 2, rather than I will say equation 2, because from equation 1 we got equation 2. So, you will get omega 0 is equal to 1 upon root over, I mean what you do is you from this equation, say from this equation 2 find out omega 0, you do little bit of mathematical gymnastic, right, and then from that you simplify, and then you do omega 0 is equal to 1 upon root over L C, then root over RL square minus L by C by RC square minus L by C. From this equation 2 you will get this expression. I suggest you please do it. I have given you the final expression. So, that one you get 1 upon root over L C, then root over RL square minus L C, by then divided by RC square minus L C. Now, circuit will be at loop. For series circuit, that omega 0 was some series circuit omega 0 was that your 1 upon root over L C only, but the parallel circuit, right. So, for series RLC circuit we have seen 1 upon root over LC. For parallel circuit one factor is multiplied and this is this factor, right. So, now when resonance will occur, that one condition is that your RL square, because your square root term your under the root, this term has to be positive. So, one condition is RL minus RC, it has to be greater than 0, RL square minus L by C, it has to be greater than 0. Another thing is that RC square minus L by C also greater than 0. This is one condition for resonance, right. So, we will get some value because this has to be positive, this has to be positive, or this one has to be negative, this one has to be negative, such that RL square minus L by C less than 0 and your RC square minus L by C less than 0. If both are negative, then it will be positive, then you will get some value of resonance frequency, right. But if let me clear it, but if your if it happens that your RL square is equal to RC square is equal to L by C, if this condition happens, then it will resonate at all frequencies, right. So now let me clear it. So this is your, that means thus the resonant frequency omega 0 of the two branch parallel circuit, this is one condition, right. It is your what you call, this factor has been multiplied. When a series RLC circuit is 1 upon root over LC, but with this factor this has been multiplied, that is I told you this multiplied, right. So now for resonant condition I told you that RL square minus L by C greater than 0 and RC square minus L by C greater than 0, both has to be positive, that means RL square greater than LC and RC square, sorry, L by C and RC square greater than L by C, or RL square minus L by C less than 0, that is RL square less than L by C. Similarly, RC square minus L by C less than 0, that is RC square less than L by C. So this way resonant will happen, right. But when RL square is equal to RC square is equal to L by C, the circuit is resonance at all frequencies, right. That also I told you, because that factor term will vanish, right. So now question is that if you solve equation 1, right, for your what you call for L, you will obtain something like this. I mean, if this is equation 1, it is very interesting. Suppose from equation 1, right, from equation 1, so your this one we call ZC square is equal to your RC square plus XC square. This is my ZC square, and ZL square is equal to R square plus XL square, right. So now let me clear it. Therefore, from this equation 1 we will see this one, that if you solve for L, you will get this, you solve it, I have done it for you, but this will solve it, you will get L is equal to half into C, half C bracket that ZC square plus minus root over ZC to the power 4 minus 4 RL square XC square. This is equation 3, right, where ZC square is equal to, this is square, right, this is square, this is square, ZC square is equal to RC square plus XC square. Therefore, ZC4 is equal to RC square plus XC square whole square. So from equation 1, you please solve this one, for your L. So let me clear it. So in this case, what is happening, that from this equation 3, that for resonance it has to be ZC to the power 4 minus 4 RL square XC square, it has to be greater than 0, because it is square root, so it has to be positive, right. So in that case you will get two values of L, right, two values of L, for which circuit will your what you call resonance will happen, right. So another this is one. Another thing is, let me clear it, another thing is, if ZC to the power 4 minus 4 RL square XC square, the this term, if it is equal to 0, you will have only single value of L, right. But if ZC to the power 4, if this term becomes negative, then there will be no resonance, right. So let me clear it. So that means whatever I told, that ZC to the power 4 has to be greater than 4 RL square XC square. The square root term, this under the square root term has to be positive, right. So we obtain two values of L for which the circuit is resonant, right. So that is, if ZC to the power 4, two values means, because here plus minus is there, So if ZC your what you call if ZC to the power 4 is equal to 4 RL square XC square, the circuit is in resonance at L is equal to half C ZC square. I mean, if ZC to the power 4 is equal to 4 RL square XC square, means this term will be 0. So that means L will be half C into ZC square, right. So that means the circuit is in resonant at L is equal to half C ZC square, and when ZC to the power 4 less than 4 RL square XL square, no value will make the circuit resonance. So this condition is there, that means under root term, square root term is negative, then its question is that there will be no value of L will make the circuit resonance, right. So this is for L. Similarly, from equation 1, second you solve for C. This is I have written, but I suggest you to solve. So again from equation 1, you solve for C. you will get another expression 2L into 1 upon ZL square plus minus ZL4 minus 4RC square XL square. If the square root term is positive, right, you will get two values of it for which circuit will resonance, right. So, and if ZL to the power 4 minus 4C square XL square is equal to 0, you will have only one value of C, right, 2L upon ZL square, at which circuit your what you call is resonant circuit, right. But if this term becomes negative, there is no value of C, that circuit will become resonant. So, this is the condition, right. We obtain two values of C for which the circuit is resonant, and if this one is equal to this one, ZL to the power 4 is equal to 4 RC square XL square, the circuit is resonance at C is equal to 2L upon ZL square, right. Again, this is for L, this is for C. Now, again, if you solve from equation 1 in RL, if you solve for RL in terms of other quantities, what we are doing is each quant variable we are trying to find out in terms of others, right. So, if you solve equation 1 for RL, you will get RL is equal to this expression. This you do it is simple, and that your what you call, if omega square LC RC square minus omega square L square plus L upon C, if it is greater than 0, then circuit is at resonant, right. So, this is for RL, and similarly if you solve for RC of the equation 1 only, you will get RC is equal to square root of RL square upon omega square LC minus omega square C square plus L by C. So, this is actually your what you call greater than 0, has to be greater than 0 for which circuit is at resonance, right. So, L, C, RL, your what you call RC, right. All these things in terms of remaining variables we got it, right. Now, question is that in these two, in 5 and 6 I told you, but here it is written here, whatever I said here it is written here, right. So, this is your what you call that it will have your resonance of your parallel circuit, simple inductive and capacitive circuit. Next, another term we define the quality factor, it is called Q, right. So, the quality factor of coils, capacitors and circuit is defined by, so quality factor sometimes for a circuit is defined by 2 pi into maximum stored energy divided by energy dissipated per cycle, right. So, for example, it is called quality factor, right, of the coils, capacitors and circuit. So, in general Q is equal to 2 pi into maximum stored energy divided by energy dissipated by your what you call per cycle. Now, for example, consider a simple your what you call your inductive circuit, that is this is resistance R, this is your XL is equal to JL omega, and this is the current flowing through I. Similarly, in figure, this is figure 1 say, this is figure 2 say, it is a capacitive circuit, it is R, current is flowing I, and it is your what you call 1 upon j omega c, that is 1 upon j omega c means it is minus your this 1 upon j omega c means it is minus j by omega c, right. So, and this is your call XC and this is your XL, XL is equal to j omega and XC is equal to your minus j upon omega c, right. So, separately we are considering. Now, the energy dissipated per cycle in the circuit of figure 1 and figure 2 is given by the product of the average power of the resistor and your what you call that is your I RMS square R and the period T or 1f. That means this is we are writing I your what you call I max by root 2, actually I max by root 2 is equal to basically your RMS value, I RMS value, right. So, it is RMS value. So, that means power loss is equal to actually this is RMS value. So, I RMS square into R, this is that your what you call that average power in the resistor, that is I RMS square into R. So, we are putting it I max by root 2 square into R, right. So, and it is your what you call that power, your average power of the resistor and the period T or 1 upon f. That means, if this is your what you call, this is your average power say I max by root 2 square into R, right, and per cycle means is multiplied by this thing. So, this is your divided by f, right. So, it is your energy dissipated per cycle in the circuit of figure 1 and figure 2. Figure 1 is inductive circuit and figure 2 is a capacitive circuit, right. So, in this case, in the case of RL series circuit, figure 1, the maximum stored energy we have studied earlier, half L I max square, that we have studied, right. Therefore, that Q is equal to 2 pi, it is maximum stored energy half L I max square. That means where we have written here the Q is equal to, that Q is equal to maximum stored energy by energy dissipated per cycle. So, in this case your this one is 2 pi half L your I max square divided by I max square by 2, because it is I max by root 2 square. So, whole square. So, I max square by 2 into R into 1 upon F, right, because this is actually energy dissipated your per cycle, right. So, F is the frequency, that is your say frequency 50 Hz means it is 50 cycles per second, right. Whenever we say F is equal to 50 Hz, that means it is 50 cycles per second, right. So, it is per cycle, so divided by F, right. So, if you after simplification simply you will get Q is equal to 2 pi F L upon R, that is your L omega by R, right. That is your Q for inductive circuit, right. Similarly, in the RC series circuit of the figure 2, the maximum stored energy is half C V max square, or and another thing is that in that your what you call that your V max with that if it is X is the your what you call reactance of the capacitor, magnitude will take, therefore V max, right, is equal to your Xc into your I max, right, that is written here. V max is equal to say I max into Xc. Now, in that let me clear it. So, this is actually half C V max square capacitor, your what you call energy stored in the capacitor, or if you use this relationship you will get half I max square divided by omega square C, right. So, in that case your in that just you substitute and put Xc is equal to 1 upon omega C and just simplify, you will get this. I am not doing it, it is understandable, right. So, this in that case in the case of capacitor, so 2 pi half I max square upon omega square C divided by same thing I max square by 2 into R into 1 upon F, right. So, if you do so, Q will become 1 upon omega C R, right. That means this is for quality factor for inductive circuit is Q is equal to L omega by R, and for capacitive circuit it is Q is equal to 1 upon omega C R, right. Therefore, a series RLC circuit and resonance stores a constant amount of energy, right. Now let us consider a series RLC circuit and resonance stores a constant amount of energy. Now, suppose this is a series RLC circuit, say VR is equal to I into R, current flowing through this is I, right, and this is my L. So, VL is equal to this is voltage across inductor is VL and voltage across capacitor is VC, and we are assuming that your what you call say for example VC is equal to V, something I am writing here, right, say VC is equal to V. Now, say this I is equal to say I m sin omega t, right, this is AC quantity. So, I m is equal to sin omega t. Now, voltage across the capacitor, that is VC is equal to V is equal to VC, just you have to integrate 1 upon C I m sin omega t dt. If you integrate, it will be I m upon omega C minus cos omega t. So, we can write that your this cos omega t is sin 90 degree minus omega t, but one minus sign is here, that means it will be I m by omega C sin omega t minus 90 degree. That means here your what you call that current I is equal to I m sin omega t, right, and V voltage across the capacitor V actually it is I m by omega C sin omega t minus 90 degree. That means current actually is leading because it is omega t plus 0 and leading this voltage V is equal to VC, voltage across the capacitor. So, we have, so that is why I m by omega C sin omega t minus 90 degree. Now, if it is sin omega t plot, I is equal to I m sin omega t plot. So, if in this case this is starting from 0, so it is your I, right. So, I is reaching the peak fast, right. So, and in this case when omega t is equal to 0, say when omega t is equal to 0, so I is equal to 0. So, this is starting from here 0. Here when omega t is equal to 0, V is equal to I m by omega C sin of minus 90 degree when omega t is equal to 0, right. So, in that case sin of minus 90 minus 1, so V will be V is equal to VC, right, that voltage across the capacitor. So, it is minus I m omega C, that is why this point is your minus I m by omega C, right. So, when current is, when current is reaching its peak, that means this angle is 90 degree. So, when omega t, let me clear it. So, when omega t is equal to 90 degree, then I is equal to I m, right. So, this is my omega t is actually, this is my your 90 degree, I is equal to I m. But when omega t is equal to 90 degree, if you put 90 degree, then V is equal to 0. So, that is why V is equal to 0, because this is the curve for V. So, V is equal to 0. So, current actually reaching its peak faster than the voltage. So, this current is leading the voltage by 90 degree. From this we can make it out easily, right. Therefore, it is written I leads Vc by an angle 90 degree. So, therefore, since when the capacitor voltage is maximum, the inductor current is 0 and vice versa. When that means when capacitor voltage, here it is, this point is 0, in this what you call this inductor current is maximum, or when inductor current is 0, this point capacitor voltage is maximum, vice versa. So, from that we can write that half C V max square is equal to half L I max square, from which we get, right, then Q 0 is equal to, may be written as omega 0 upon L I r, that is 1 upon omega 0 C r, right. So, actually your what you call, from if half C V max square is equal to half L I max square, from that you then you that Q 0 is equal to your L omega 0 by r is equal to 1 upon omega 0 C r, right. So, from this your what you will do, right, this is the equation, right. So, little bit you try to do yourself, right. Many things I have done, I have been spending lot of time, right, little bit you do that, but one or two thing I am telling. Suppose this is my Q 0 is equal to, I mean you write separately, say Q 0 is equal to omega 0 L by r, and again you write Q 0 is equal to 1 upon omega 0 C r. Now, Q 0 into Q 0, that is Q 0 into Q 0, then omega 0 L upon r into 1 upon omega 0 C upon C r. So, omega 0 will cancel, right, or finally it will become L upon r square C, the Q 0 square will become L upon r square C. So, let me clear it. This is an exercise for you. To do this little bit, right. So, now if you so this is your Q 0, right. Now, question is that suppose before coming to this figure, suppose at omega 0 current is maximum, because for your what you call, for resonance circuit we have seen that your at the resonant frequency series RLC circuit, say that XL is equal to XC. So, in that case that your current is maximum, and this current, say it is I 0. I 0 is the maximum current at resonance frequency when omega is equal to omega 0 or F is equal to F 0, right. So, since the power delivered to the circuit is I square R, therefore, at I is equal to, we know that power I square R is the power delivered to the circuit. Therefore, suppose at I is equal to I 0 by root 2, say the power is 1/2 of the maximum value which occurs at omega 0, right. Suppose your this one we know I square R, right. Now, when I is equal to say I 0 by root 2, then if this is the power loss P is equal to when I is equal to I 0 by root 2, then it will be I 0 square R by 2, that is it will be half P by 2, right. So, let me clear it. So, this is I 0, this is your I 0 and this is your I 0 by root 2, right. I will come to this. So, power delivered to the circuit, the power is 1/2 of the maximum value which occurs at omega 0, right. Therefore, that means whatever at resonance power is I 0 square say R, I square R is equal to, if I is equal to I 0, then I 0 square R, but at I is equal to I 0 by root 2, it will be half, right. So, the points corresponding to omega 1 and omega are called the half power points. So, this is actually this one, this is your I 0 by root 2, this is called half power point, because power loss is I 0 square R, but if it become I 0 by root 2, it will be I 0 square R by 2. So, P by 2. So, this is called half power point. So, this is at frequency, say this is your omega is equal to say omega 1, it is intersecting 2 point of this curve, and this is your what you call omega 2 or f1, f0, f2 or omega 1, omega 0, omega 2. The difference between this difference between these two, that is your what you call this from this to, I mean this width from here to here, it is called your bandwidth, right. So, that is your omega 2 minus omega 1, or if it is in radian per second, or if it is in hertz, it will be f2 minus f1, right. And this is your resonance frequency. This is called actually bandwidth time, right? And this omega, when your omega is equal to omega 1 means for series RLC circuit we have seen, right, that your what you call that your XL and XC is your what you call greater than XL, or other side your what you call XC less than your XL, that we have seen. So, these 2 points called half power point, and this distance we call bandwidth, right. And this is, if it is omega radian per second, if it is frequency, then it will be in hertz. So, this is, so at half power frequency the net reactance is equal to the resistor. This is written at half power frequency, net resistance your what you call is equal to the resistor, because here I am making it for you. Suppose Z is equal to your R plus J for series RLC circuit, XL minus XC. Two things can happen. If one is XL minus XC, it may your what you call, because it is half power frequency, may root 2 has to come, right. So, it will be your XL minus XC may be R, or XC minus your what you call another thing will be XC minus your XL may be R. Two condition may happen, right. So, in general, if we take first condition that XL minus XC is equal to R, ultimately mod XL minus mod XC is equal to actually R, right. Therefore, Z is equal to one condition if you take, it will be your what you call R plus JR. That means, this one will be your what you call root 2 R angle 45 degree, and if Z is equal to R minus JR, it will be root 2 R angle minus 45 degree, either of these, because mod XL minus XC is equal to R. This is either one condition, this another condition, right. So, let me clear it. Therefore, at half power frequency the net reactance is equal to the resistance, right. So, that means a circuit with high Q will have a very sharp current response, and response curve as compared to one which has a low value of Q. So, your what you call several your admittance versus angle, other graphs are shown, frequency, right. From that you can easily justify this one. Similarly, that I told you it will be mod XL minus XC is equal to R. Since at omega 1 the circuit is, I told you have very beginning of this topic. Again I am not going to the figure, when your omega is equal to your what you call at omega 1, which is on the left hand side, right, of that curve. So, at that time XC greater than XL, right, XC greater than XL. So, XC your greater than XL, therefore, at omega 1 XC minus XL is equal to R, right. And similarly, at omega 2 when it is going to the other side, XC less than XL or XL greater than XC. So, in that case XL minus XC is equal to R. Say this is equation 1, this is equation 2. See, previously I have explained this, right. Whenever you, I suggest whenever you go through a video lecture, first draw those diagram, and after that you just go through this that video lecture, then it will be easy for you to make it on the notebook. So, if these two conditions hold, therefore, the corresponding impedance I told you, one will be at omega 1, Z1 will be R plus JXL minus XC, that will be R minus JR, that will be Z1 will be root 2 R angle minus 45 degree, because it is root over R square plus R square, and angle will be tan inverse minus 1, because it will be tan inverse your minus R by R. So, it will be minus 45 degree. Similarly, at omega 2, Z2 will be root over root 2 R angle 45 degree, right. Therefore, at omega 1, I1 will be that V angle 0, this is the voltage reference, right, divided by your impedance root 2 R angle minus 45 degree, that will become V upon root 2 R angle 45 degree, right. Similarly, at omega 2, your I2 is equal to V upon root 2 R angle minus 45 degree. Since V by R is equal to I0, because at resonance XL minus XC is equal to 0, and for which current is maximum. If XL minus XC is 0, so Z will be simply R, therefore I0 the maximum current, right. So at resonance, that is V upon R. So the current at resonance will be your frequency at omega 0. Therefore we can write I1 is equal to your, this is 1 upon root 2 is there. So and I mean this one 1 upon your this term, if you can write, it will be basically this term, you look at this term, if you see, it will basically V by R upon I0 divided by root 2 angle 45 degree, that is your 0.707 I0 angle 45 degree, right. So this one, therefore I1 is equal to 0.707 angle I0 angle 45 degree. Similarly I2 is equal to 0.707 I0 angle minus 45 degree. But at omega 1, at omega is equal to omega 1, XC minus XL is equal to R, right. Therefore that means whenever, that is at omega is equal to omega 1, right. So omega is equal to omega 1. So in that case your XL will be L omega 1 and XC will be 1 upon omega 1 C. So here you put this, and this is say equation 3, right. So let me clear it. So similarly at omega is equal to omega 2, similarly, so XL will be L omega 2 and XC will be 1 upon omega 2 C. This is actually, when you are writing at omega 2, means it is omega is equal to omega 2. So this is equation 4 and this is equal to R actually, right. So now what you do, subtract equation 4 from equation 3. I mean this equation you subtract from this equation. If you do so, you will get 1 upon omega 1 plus 1 upon omega 2 your by C minus your what you call omega 1 plus omega 2 into L is equal to 0, or simply you will get 1 upon omega 1 omega 2 is equal to LC is equal to 1 upon omega 0 square, because omega 0 is equal to resonance frequency is equal to 1 upon root over LC. If you take the square of it, so LC will be is equal to 1 upon omega 0 square. So that is what we are writing here. Therefore omega 0 will be is equal to root over omega 1 into omega 2. This is a good your relationship and easy to remember, that omega 1 is this side and other side. So omega 2 minus omega 1 is the bandwidth, and omega 0 will be your what you call root over omega 1 omega 2 geometric mean, right. Similarly you add equation 3 and equation 4. Already equation 3 equation 4 we have got it. So add these two equations. If you do so and simplify, you add and simplify, you will get omega 2 minus omega 1 upon omega 1 omega 2 C plus omega 2 minus omega 1 L is equal to 2R, right. Therefore your omega 2 upon simplification, you take omega 2 minus omega 1 common. So you will get omega 2 minus omega 1 your 1 plus LC omega 0 square divided by your omega 0 square C. Now LC omega 0 square is equal to 1, because omega 0 is equal to 1 upon root over LC, you know. Therefore if you square it, omega 0 square is equal to 1 upon LC. Therefore cross multiplication, omega LC omega 0 square is equal to 1. So this term you put is equal to 1, such that 1 plus 1 you are getting 2, right. So let me clear it. So if you put that, will be omega 2 minus omega 1 is equal to 2, both sides will be cancelled, it will be omega 0 square CR, right, or that divide, it is omega 0, so divide by omega 0. So omega 2 minus omega 1 upon omega 0 is equal to omega 0 CR. This we have seen is equal to Q0, we have seen 1 upon omega 0 CR. So it is 1 upon Q0, or Q0 is equal to W0, another expression of Q0 is equal to W0 divided by W2 minus W1, right. So it is basically W0 by BW, bandwidth. So this is equation 6, right. So these are your what you call, these are the things, certain things, it is very simple thing. Only thing is that little bit of understanding and mathematical your what you call mathematical exercise there, but these are the very simple thing, right. So that means we get this equation, that omega 2 minus omega 0 is this one, or this thing your what you call this Q0, your Q0 also can be written as omega 0 by Bw, that is the bandwidth, and Bw is equal to omega 2 minus omega 1, right. Thank you very much. We will be back again.